agenda is to make you understand the basic difference between jump and call. We have two instructions, very famous instructions in 8086. One is jump and other is call. The second point, there are two types of subroutines or function calls that we can do. One is near and another is far. What makes the difference between these two types of function calls also we are going to see, and the related syntaxes also we are going to see. Point number 3, arguments and return value. This is very, very important. You can't learn functions without knowing how to pass argument and how to send return values back to the calling function. Finally, we'll see a program and we'll also execute that program in 8086 emulator. There exists one pointer called as instruction pointer, also called as IP. This is most widely called as program counter, which holds the value of next instruction that is going to be executed. Holds the address, holds basically the address of next instruction that is going to be executed. For an example, look at the program which has 10 lines. Every line has its own address, starting from 2000 to 2010. Of course, there are 11 lines, starting from 2000 to 2010. The starting address of the program is 2000. Okay, so when you start executing this program, you can execute this program or you can come to the value 2000 only because of IP. Who is providing that value to you? IP. What is IP? It's an instruction pointer. What exactly it is? It is a register. It's an inbuilt register in your architecture 808, which always holds some address. That address is the address of next instruction that is going to be executed. So when I'm executing this instruction 2000, your IP will have definitely the value 2001. When I come to 2001 and when I'm executing the instruction that is placed in 2001, your IP is already incremented to 2002. The moment I'm executing this 2001, okay, the instruction at 2001, at that time, the value is already available in IP, that value is 2002. It means that whenever the current instruction is being executed, by the time itself, the value of IP is incremented by 1. Okay, it means that by 1, the meaning is that 2001, 2002, 2003, and it goes on. Your program always executes sequentially. The instruction pointer is always incremented by 1. At 2003, we have an instruction called as jump demo. For our instruction or for our understanding, I've written jump as JUMP, but in 8086, that is not JUMP. The instruction name is JMP. How do you jump to any location, any label? Whenever you have written JMP, jump demo, demo is the label name. This is your current instruction 2003. When you are executing this instruction, what is your IP value? Obviously, the IP value is 2004. What your machine understands, the moment you are executing 2003, it is expecting you to come to this way. Actually, the program is always executed sequentially. But unfortunately, whenever you have jumps or loops, you don't execute sequentially. Sometimes you will rotate cycle and you may jump to some other location. Unfortunately, you have JMP jump demo. Your IP value is 2004 now. The moment you jump to demo is at 2007. Demo is the user-defined name. That name is for sake of programmers. But in fact, the machine uses the address 2007. So whenever jump 2007 is understood by your architecture, this instruction is decoded. Immediately 2007 is updated in the IP value. The current IP value is 2004. Now it is updated to 2007. Since it is updated to 2007, immediately the control will fall to this way, 2007. Because you yourself intentionally written jump demo, it means that you wanted to go to some other location, this label 2007 location. So as soon as you come to this location 2007, here onwards the IP value will be incremented as 2007. When the moment you are executing the instruction that is related to 2007, IP is incremented to 2008, 9, 10, and it goes on. So the point that I wanted to convey is that whenever you jump to this particular label, and then the IP incrementation is done in this way. Your 2004 is never available. When 2004 is overwritten by 2007, there onwards, so the incrementation done from 2007 only, because your intention is to execute from here. You wanted to skip these instructions. That's why you have written jump. There are some conditional jumps, there are some unconditional jumps. Depends upon the situation, depends upon the program. We may shift whenever you are jumping from one location to other location. Okay. IP changes to 2007 from value 2004 to 2007 it changes. This is what internally happens, and there are no stack operations. No stack operations takes place. No stack is required here to do this operation. Only IP value is changed from existing value 2004 to 2007. That's all. No stack operation takes. There are two types of jumps. Whenever you perform conditional jumps or unconditional jumps, this is what that is going to happen. Now let us see how subroutines or functions or closures in 8086 internally gets executed. Okay. If so as to understand the functions with arguments and return values or subroutines, this concept, this entire presentation, it's very important for you to understand this slide. I may take around 5 minutes to demonstrate this slide. Please listen carefully, sit tight, concentrate on this particular slide. Look at the program. We have some set of instructions here. Some set of instructions starting from 2002, some 2020. I started executing this program. While I'm executing 2000, my IP value was 2001. I came to 2001. While I'm executing 2001, meanwhile, the IP value changed to 2002. While I'm executing 2002, it became 2003. Like that, I came up to 2000. While I'm executing 2006, actually the IP value is 2007. While I'm executing this one, the moment I come to 2006, what is the IP value? If somebody asks you, when I'm at 2006, what is the IP value? The next instruction, what is the, by default, what is the next instruction in sequence that you are going to execute? 2007. So your IP value is 2007. While I'm executing an instruction at 2006, the IP value is 2007. Good. As of now, it's fine. What is the instruction that is there at 2006? At 2006, while I'm executing this instruction, the IP value is 2007. The instruction that is placed here is called demo. This is the function call. It is not jump. This is the function call. The major similarity between jump and function call is same. Immediately the control is shifted to the address location of the label that you have mentioned. Okay. In jump, demo is the label name. In call demo is the function name. That is only the difference. Okay, both are addresses only. Both are address. In the previous case, I jump to the location 2007. Here I am jumping to the location 4000. I'm jumping to the location 4000. Of course, it's a function call. Call demo. Demo is a keyword that is for our purpose, but actually it's an address. The address is 4000. You are going to this particular location 4000. Now, do you know one thing? If you want to go to this location and if you want to execute that instruction at 4000, then 4000 value has to be placed in instruction pointer or program pointer. So who does that one? Immediately whenever this particular types of instructions are there, call demo or jump demo, immediately the IP is updated. When IP is updated, the value 2007 is overwritten. I repeat, the value 2007 is overwritten. So never you will have 2007 again. The moment you come to 4000, the sequence of execution will carry on like this: 4000, 4001, 2, 3, 4, 5, like this. But after some time, do you want to come back to the calling function or not? Definitely yes. Am I right or wrong? This is not jump. Okay, this is the major difference between jump and function subroutine. Okay, in case of jump, you'll go to 2007 in my previous slide. Okay, okay, the moment you go to 2007, you have updated 2004 to 2007 and started executing from here. There's no problem. That was actually your intention to do that. But here, in this case, the moment you came from 2006 to 4000, okay, you started executing 4000 onwards. That's fine. That's good. But at some point, when the moment you are returning from the function, you have to get back to 2007. Definitely you have to get back to the calling function. That is the nature of the function call. In the calling function, you made a function call, you executed it, and you should come back to the calling function. Okay, but you have overwritten this value 2007 with 4000. You can never come to this particular location if you do not provide 2007 while executing instruction at 4004. You have to provide the instruction 2007, so that only holding that address you'll come back to this location 2007 and keep carrying. You could carry on the normal execution of your calling function again. That means calling procedure. This will happen using stack operations. Okay, this is automatically done by your call procedure. The moment you made call demo, your IP is of course changed to the value 4000. Before it is changed to the value 4000, the existing value, that means the return address, it is the return address. The return address is stored in stack. That's why a push operation is used. In my previous slide, I have shown you one statement. In jump, we don't use stack operations, but in call, we use stack operations. Okay, so here we push the IP address. That means during execution of 2006, what is the IP address that we have? 2007. That IP address will push to top of the stack. Now 2007 is preserved in top of the stack. That means stack, using stack. Stack is a separate memory that we could use in our program. So it is separately available in stack segment. Stack operations are already demonstrated as part of online classes. I hope you have followed those classes. So I'm pushing the IP value to the top of the stack. Means that I'm preserving this value. The moment I started executing the function, the moment I come to 4004, now I want to get back to this location 2007. Now I need to pop that IP, pop that value to IP. Okay. So pop from stack. From stack, I wanted to pop that value to IP. Okay. So internally it is written as pop IP. When I write pop IP, it means that current IP up, current top of the stack, 16-bit information will be popped and stored in a register called as IP. Okay. And one important thing, in the program, we don't write push IP or pop IP. Okay. These are internally carried out by call demo. This is quite intelligent. This is brilliant. Okay. Whatever these hectic internal things has to be done will be done by call demo only, subroutines only. We need not to do. So why I'm explaining these things, you have to understand how these procedures are executed inside. This understanding is very, very important. This is for just for our understanding. In our program, we'll just simply write call demo only. Okay, but push IP, pop IP will be automatically performed by call demo. That means your subroutine concept. Okay, right. I hope this point is clear. Now we'll go to the next slide. In this slide, you are going to learn the types of functions or subroutines and syntaxes that are related to functions. Okay. Before I come to syntaxes, let me show you. Let me show you something important. There are two types of function calls that happens that could take place in 8086. Okay, there are two types of function calls. Basically, in high-level languages like Python, Java, C, we don't use these keywords. These type of function calls never exist. Okay, they exist internally, but we don't know. We don't know as of now. These types of function calls will be definitely there. Okay. Those types of function calls are called as near and far. Okay, there are two types of function calls that could happen. Okay, but this point need not to be demonstrated as part of high-level languages or C languages. Near and far function calls will be taken care by your compiler, high-level language compilers. That's why this point is not explicitly demonstrated as part of C language or Java language or Python language. But whenever you are reading procedures or subroutines concepts in 8086, you have to manually operate on type of function calls near and far. That's why these keywords are demonstrated. What is near call and what is far function call? Whenever you are making a function call, you have to tell whether it is a near function call or far function call. Near function call means you know that there are totally 16 segments in 8086 memory. Your total memory is 1 MB. In 1 MB, there could be 16 segments. Out of 16 segments, only 4 segments are active. The active 4 segments are core segment, data segment, stack segment, and extra segment. Okay, right. Your function code is usually written in core segment. Okay, sometimes you may write because since there are 16 segments, 4 segments are active. Okay, out of 4 segments, 1 is core segment. In the core segment, you can make a function call whose function's definition is written somewhere else, not apart from the other segment. I mean, apart from the current using the segment which is being in use. Okay, for an example, you have 4 segments that are being in use, and remaining 12 segments inside your memory are inactive. Okay, your function definition may be available in any one of the inactive segments. Okay, still you can make them active the moment you make a function call. Okay, this type of function call is called as for. It means that whenever your function's code is not available in the current working code segment, okay, your function's definition is written outside of the current working code segment. This type of function call is called as for, FAR, for. It means that you are telling, dear computer, my code is not available right here. It is available somewhere else. Please go and get it. You will provide that address also. Okay. So this is called as for. Okay. It is far away from the current code segment. That's why the name for. The another type is near. In case the function code nicely, very easily, if it is available within the same code segment, then that is called as near. Okay, very often you will see the more function calls are near, and very rarely you will see the function calls that happen using for statement. Okay, near means the function definition available in the same code segment. For means the function definition available in different code segment. Okay, now we'll see the syntax. Now syntax while making function call is similar for these 2 types of functions. Okay, you simply use the keyword call and use the label name. That means the name of the function. Okay, demo, call demo. This is called as function call. Okay, while writing the function definition, you will say whether this is a near function call or for function call. Okay, right. You will say demo, project, near. Okay, if you have placed your function code somewhere else in the other code segment, and if you are pretty much sure that some other code segments are going to be accessed, going to access that function code, then you need to write, while writing that function definition, you have to write it as demo proc, PROC means project, near. Okay, in near means within the same function call and within the same code segment. Other code segment, if you are writing, then demo, procedure, for. The syntax will be for. Okay, if it is near, near. Okay, very often you will see near function calls. Very rarely you will see for. In the example that I'm going to demonstrate, I have used near only. Okay, right. So how do you basically identify, or how do you 8086 basically identifies whether it is a near function call or for function call? It depends upon the address. Okay, so every instruction, you know that 8086 is a 20-bit address. That means every instruction, including function call, including move instruction or whatever, will have 20-bit address. 20-bit address can be represented using 5-digit hexadecimal. Okay, right. You will have a code segment. Code segment is 16-bit. Code segment address is 16-bit address. Okay, in code segment the value is 3000 for an example. Okay, in this code segment you have 2 functions. One is near function call and the other is for function. Okay, you have function 1 and function 2. Function 1 address is quoted in 5-digit hexadecimal. That means this is 20-bit address. Okay, 32000H. This is 5-digit hexadecimal. 5-digit hexadecimal is equivalent to 20-bit binary number. Okay, and another address F2, another function like function 2, whose address is 54000H. Okay, by looking at these 2 addresses, okay, these 2 addresses, your computer can identify which of these 2 is for function call and which one is near. Okay, and it compares the first digit with the code segment value. The code segment actually started with 3000. Okay, your function calls address is 32,000. It means that function call offset is 2000 and code segment is 3000. Okay, 3000 into 10, that means 30,000 plus offset 2000. Totally it is 32,000. Okay, this is the address. So this function 1 is available within the same code segment. That is the meaning. Okay, but whereas in function 2 it is 54,000. 54,000 means the code segment has started at 5,000, offset started at 4,000. 5,000 into 10 is 50,000 plus 4,000 is 54,000. So this 54,000 instructions address is not available in the current working code segment. The current working code segment has started at 3000. It's not started at 5000. That's why function 2, it understands that function 2 is available at somewhere else 5000 but not at 3000. It understands this function as for. Okay, right. Based on this demonstration, look at this slide for 1 minute and try to answer the question. Everybody, please look at this slide. There is a question. Please try to understand the question and answer it. All right, look at here. Okay, you have to identify near and far function calls. Given the code segment started at 3000, okay, you have given 3 function calls, f1, f2, f3. The starting address of f1, f2, f3 are also given. Okay, 5-digit numbers, that means 20-bit addresses are given. Good, every information is available now. Okay, now look at these addresses and tell me which of these functions are near and which of the functions are far. 3, 4, 5, 6, 7. When the moment you have seen 34,000 some change, okay, since your address started at 34,000, okay, 3, okay, your code segment started at 3000. 3000 into 10, 30,000. 30,000 plus this is offset. 4, 5, 6, 7 is offset. So F1 belongs to this code segment. Okay, so F1 is near to this code segment. Now look at this F2. F2 started at 45,600. 45,000, that means 4,000 is code segment address, 5600 is the offset address. Code segment 4,000 into 10 is 40,000, offset is 5600, that means total it is 45,600. So since the code segment address of F2 is 4,000, it is different from the current working code segment. That's why F2 is for function call. It's for function call. Okay, now coming to F3. F3's address is 31,000. It's very simple. So it started at the code segment address of this F3 started at 3,000, which is relevant to this particular code segment. So F3 belongs to this particular code segment. That means F3 is near. So the question's answer is very simple. F1 and F3 are near function calls. F2 is far function call. Okay, right. Now, procedure call subroutines with arguments and return values. Everybody, whomever in this particular room, here onwards, whatever you are going to see, the upcoming 10 or 15 minutes is very, very important. Please listen carefully. Okay. You might have used function calls in your C language, C++, Java, Python. You might have studied at least 3 to 4 programming languages as of now. So at least C or Python, 2 languages you should have studied. So in both the languages, you have used functions. Wherever you use function, you are using, wherever you are using function, within 10 minutes, I'll try to wind up this particular session. Okay, before that, please listen carefully. Wherever you use function, you will be using arguments. For an example, you may be using demo arguments A1, A2, 2 arguments you are passing to the function called demo. Okay, so here arguments like parentheses A1, A2 or A comma B, demo A comma B, like that parentheses and argument names we cannot specify in 808. Basically, we have to use stack. The moment before you are making a function call, if you want to send any arguments, those arguments you have to place in a stack. Using stack, the moment you went to the function, okay, you have to pop the values from the stack and you have to use inside the function. This is how the arguments are passed from one function to another function. There are no parameters, there are no parentheses, there are no parameters concept at all. If you want to share any parameters to the function, then you have to push those values to the stack. Stack memory can be accessed by other functions. whenever you made a function call, the moment your control is shifted to other function call, in that particular function, you have to use pop, and you have to use those arguments using pop operation, using stack only. Okay. For an example, if I want to pass variables a comma b from my calling function to other function, then what I do is that I will push both a and b into the stack, and then I'll make a function call. Immediately my control will be shifted to that particular function call. In that function call, I'll perform pop operation on stack, and I'll access both a and b values from that particular stack memory. Okay, it's not that parentheses, okay, formal arguments, actual arguments. This concept is not there in 8086. Of course, that actual arguments, formal argument concepts in C language or Java language is just for our convenience. That is the user friendliness that is provided by us to us by the Java language environment or C language environment. But in fact, every function call happens like this. Every function call, the stack memory is used for including arguments, including variables. Everything is stored inside the stack only. Okay, right. Look at here. I'm going to execute one small program where I'll be using ABCD, 4 variables, string variables. ABCD are the 4 string variables. Okay, I wanted to pass ABC to one function. Okay, inside that function I'll access ABC. So if I wanted to access ABC, for that reason, what I do is that before I make a function call, I'll place A, B, C on the top of the stack. The moment the function call is happened, the return address will be kept at the top of the stack. So inside the function, I'll have A, B, C, and the return address. It's very important to preserve my return address because that is available in the top of the stack. That return address I'll store in any 16-bit register. Once after storing that return address in any 16-bit register, I'll start popping C, B, A. I'll access this C, B, A inside the program, inside my function. I'll print the values of C, B, A. Of course, the values will be printed in reverse order. You can see the values are pushed in A, B, C order during printing the values. Okay, so as to make you understand that I used a stack, I'll print the value of C first, and then B next, and then A next. Okay. And afterwards, using this A, B, C, the return address that I stored inside the stack, that I'll keep in the stack again inside the function, because if I don't place, then I will never get back to the calling function again. So whatever the key statements that I made now, those are written. Okay. In case whenever you are reviewing this particular or revising this particular PPT, what are the statements that I taught so far are written, you could study them later on. Okay, now let's execute the program. Inside program, I'm using 4 variables A, B, C, D. Only A, B, C are passed as an arguments to the function by pushing them into the stack. Inside the function, I'll access C, B, A in reverse order because it is stack pop operation. And I'll access them, I'll print the values, and then I'll place the return address as it is into the stack, and so that I'll coming back to the calling function. To know whether I have come back to the calling function or not, the additional variable, that is D, that I'll print the value of D in the calling function, not in the called function. In the calling function, I'll print the D. Now let's in the program, as I told, I have taken the variables A, B, C, D, 4 variables. Okay, so this A, B, C I wanted to pass to the function. Okay, what is the function name? Okay, demo is the function name. Using the near function call, I made the function call. Where did I perform the function call? Here. Okay, so before I perform the function call, okay, and I performed push operation. Okay, I performed push operation. What are the things that I'm pushing? Push A, push B, push C. Okay, I performed the push operation. The moment I come to this particular function, I'm popping BX. What is the top of the stack? Top of the stack is the return address, because I have to get back to this particular location the moment I call this function. Okay, this is my calling function. In the calling function, I have to come to the highlighted instruction LEA DX, D. I cannot come to this instruction if I don't preserve the return address. That return address is preserved in BX. Finally, I will push this BX into the stack. Okay, that ABC in reverse order I have accessed, and I'm printing using interrupt 21H. That means the value of ABC will be printed on the screen. So ABC, A says the first argument, B says argument 2, C says the argument 3. While I'm printing, argument 3 is printed, argument 2 is printed next, argument 1 is printed next. Okay, that means 3, 2, 1 will be printed in reverse order because I have performed a pop operation. Pop operation is just reverse to push, you know that one. So finally, I'm pushing BX back to the stack. Okay, when I execute this instruction, you should see that A, B, C are pushed into the stack while popping. This C will be popped. That means you will see first argument 3 is printed, and then of course it is second argument, but the keyword first is repeated. But anyhow, number makes the differentiation. 3 will be printed, and then 2 will be printed, and then 1 will be printed. I'll get back to the after execution return. I'll get back to this particular function call again. So here I'm placing D in the dx, and I'm printing the D value. That means after function call, you should see that return from the function. Okay, so I'm executing this function. I'll go with direct execution run. I'll directly run this program. Okay, look at the output. So first argument, that is 3. It means that it is a value of C. And the second one, first argument 2. Actually, I should have written it as second argument. But anyhow, the number differentiates it as the second value. That means B value. This is B value. This is A value, the next thing. First argument is 1. 1 means A value. 1 means A value. So C is printed, B is printed, A is printed. Finally, I have returned to the function, and in the main function, in the code segment, whatever the leftover instructions, printed returned from the function. So this is all about the subroutines and uses.
It is possible for us to host and upload many demanding courses on this YouTube channel only if you support us by subscribing. Please subscribe, switch on the notification bell, stay connected, and enjoy learning.